Okay, so people, here's what we're going to do. We're going to talk about objects falling and how gravity works. And one thing I would start out with you from the very beginning is to say that you may think heavier objects fall faster, but they don't. I'm going to show you a really quick clip to prove this. Now, what is the reason that a feather would fall more slowly than a bowling ball? And you may think, hey, the reason is the bowling ball is heavier, but that's not it. What is the true reason? And we'll discover that first by looking at this little video clip. Now in this clip, you're looking at a blurry image of a control room at NASA, okay? Now what they're about to do is drop a bowling ball and a feather. But at NASA, they have this massive facility that they've sucked all the air out of, and they made it a vacuum. So let's see what happens in this vacuum. Here's the feather, here's the bowling ball. And since there's no air in here, the feathers and the bowling ball are falling at exactly the same rate. Okay? So the reason you may think, the reason you feel that heavier objects fall faster than lighter objects, or would fall faster, is the air. The air is messing up your perspective on gravity. Next thing I want you to understand is that when we're talking about gravity, and here's some problems we're going to be doing later. When we're talking about gravity, there's a magic number. And that magic number is right here. The acceleration due to gravity on Earth is 9.8 meters per second per second. Now, I'm sure many of you were unaware that I was such an excellent artist, okay? But clearly, this is a rendition of me, okay? And what I'm doing in this picture is I'm bouncing a tennis ball off the concrete. And the tennis ball is going to go up, and then it's going to fall. So let's talk about this tennis ball. First, if I drew, like a particle diagram of it, it originally would be going faster, so there'd be more distance between the ball each time, right? And the velocity is originally greater, and the velocity of the ball gets less and less and less until eventually, change my picture a little bit, until eventually the ball would have to have a velocity of 0 up here at the top, right? The velocity at the top would have to be 0. And then, as the ball fell, its velocity going down will be exactly the same as the upward velocity it had. In other words, the falling ball, its velocity at each point in time, or at each place along the drop, will be equal and opposite to what it was doing on the way up. So what goes up, what must come down. The other thing we need to know is that the acceleration here the whole time is 9.8 meters per second down. So the whole time the Earth is pulling this thing towards the ground. Now, what does acceleration really mean? It means an acceleration of 9.8 meters per second means if you have a ball and you let go of it, I'll make sure I'm on screen up here. If you have a ball and you let go of it, when you let go of it, its initial velocity is 0. And on Earth, 1 second later, the ball will have a velocity of 9.8 meters per second. And then if it fell for another second, its next velocity would be 19.6 meters per second. So in other words, every second that goes by, the ball increases its velocity by 9.8 meters per second. That's what acceleration is. So there are some formulas here that you should write down that you're going to be using today. You'll use these formulas with your worksheet, on your Edpuzzle, on this Edpuzzle. Acceleration on Earth is 9.8 meters per second per second. Acceleration is equal to change of velocity over time. And now change of velocity just means the difference, the final velocity minus the initial velocity, okay? If we're talking about the distance something goes or the distance it falls, you can use xf equals 1/2 at squared. And don't forget, if we're talking about gravity, that a is always going to be 9.8. And then down here at the bottom, you may end up with a problem where you can combine these two into one formula, which is vf squared equals vi squared plus 2a delta x, or in other words, the change in distance, or how far you've gone. So this formula is really these two formulas combined. Okay? Let's go outside and let's bounce a tennis ball. Okay, so we're outside in front of the school, and I'm about to bounce a tennis ball, and you're going to be able to see it. Now, I may bounce it so hard that it goes out of the top of the screen, but all that matters is that you can time it from where it hits the ground, and then it hits the ground again. Now, if you can time that at home, and don't worry, you can play the video over and over, but if you can time that, then we'll be able to calculate together how high the tennis ball actually went. Doesn't matter if you see the top. Okay? So here we go. We're going to use the second one because I'm afraid the first one may have gone out of screen, so them's the breaks sometimes when you're filming live. All right, so we're back upstairs. Now, this Edpuzzle may be a little difficult for you because I'm going to ask you some questions that maybe you haven't seen before. But you're going to just have to use like your fundamental understanding of the world to try to get it. I'm going to try to lead you to the answers, but I'm not going to give them to you, okay? Now first, here are the problems we're going to use. I went out there and I bounced this ball, okay? I bounced it. Now whether you saw the top of the bounce or not, it doesn't matter because I haven't looked at the video yet. But what I will say to you is this. How long was the ball in the air? Okay? Now, I don't know the answer to that, so I'm not going to make that a question. But the bigger question is, how long was the ball in the air? And then, therefore, how long was the ball falling? Okay? Now, the answer to that is, it was falling for half of the time. So, whatever math you got, and I hope you checked it a couple times to get a really good number, well, however many seconds the ball was in the air, it was falling for half of that time because it went up for half of the time and then it fell for half of the time, okay? So now watch what I'm going to do. If we just think about the ball falling, okay? We're just going to think about the ball falling, all right? And we're using the time as half of the total time that the ball was in the air. Then we can tell boom, using this very simple formula, how fast the ball is going right before it hits the ground. My question for you is, what number are we going to know? What number is A? We know the number for A all the time. That's right. And then what number will we put for T? That's right. We'll put half of the total time in the air. So 9.8 times half of the time. Okay? So that's pretty good. Another thing, I will ask you this later, very simply. What if I wanted to know what the total height of this was? What is height? What is height measured in? Yeah, it's measured in meters, and height is distance, right? So if height is distance, which one of these formulas solves for distance? 1, 2, 3, or 4? Yep, this one right here. Right? So we can use this formula to calculate how high the ball, what the height of the ball's bounces. We didn't even need to see, we just need to see the ball hit the ground here and then hit the ground again. We can take half the time, slip it into this formula, xf equals 1/2 at squared. And xf is what we're solving for. 1/2 a is always going to be 9.8. And then this t, the t squared, is going to be half of your total time. Half of the total time that the ball was in the air total. So this is just the falling time that you will square. And again, I don't know what number you got. Does that make sense? So I'm going to ask you for these numbers later. All right? Now, there are also other problems I could ask. I could say, hey, after this ball, after any tennis ball goes flying up in the air, what is its speed at the top? What is its velocity, its vertical velocity at the top? That's right, it's 0. It's got to be v equals 0 up here because it goes up, then it stops, and then it comes back down. So now, understanding that, I could say, hey, if this ball fell for 1 second, how fast would it be going? And you would say, I remember it's 9.8 meters per second. Correct. What if the ball fell for 1.2 seconds? Which formula would you use? That's right, you would use this. If you want to know the velocity of the ball after falling for 1.2 seconds, you would say A is equal to delta V over T. 9.8 meters per second is our A. The change in velocity is what we're looking for because we know the original velocity at the top was 0. And then how long has it fallen for? 1.2 seconds. Boom. 1.2 times 9.8 would give us the answer to this one. Does that make sense? That'd be a little less than 12, like 11.6 probably. Just guessing, I don't remember. But does this make sense to you? Then you're going to click yes. In the end, I could end up asking you to use this formula, but I doubt we'll use this formula today. It's an easy formula to use. With this formula, I could say, if the ball fell for, let's say the ball fell for 3 meters, how fast would the ball be falling after 3 meters? Then you would use this formula right here. The VI would be 0. The VF is what you're solving for. 2 times A, the A is always going to be 9.8, right? And then the distance it fell, that's going to be 3. Does that make sense to you? All right. So we're going to wrap this up. Gravity, 9.8 meters per second. Things go up and things go down. They match each other up and down, right? At the top, you have a velocity of 0. These are the formulas you can use to solve any of these problems.